Yeah, you can start.
Okay. Let's wait for a minute more. 9:35. Let's start at 9:35.
The stream is live though.
Fine, that's okay. Oddly enough, I get YouTube notifications of the stream is live. The Android notifications. Yeah. Okay, let's get started. So today will be sort of more of a primer on probability and certain basic probability inequalities and stuff. But to begin with, let's recap. I think I went a little hasty towards the end of last lecture. So I'll quickly recap what we did last lecture and sort of say where it fits in the product. This one, so recall from last lecture. We had introduced the notion of talked about pairwise independence and how this might help in reducing the amount of random points we use at times. Particularly, what we actually defined was this object, although I didn't use this exact term. I think somebody in the audience, I think Varun mentioned this. So actually, let me formally say the object which we constructed is what is called a pairwise independent family of hash functions. And what is this? So a family of functions, a family H of functions from, say, some domain of size n to a range of size m is said to be pairwise independent family if two conditions are satisfied. One, if you pick a random h from this family, it's a collection of functions. It's not the collection of, it could be the collection of all functions from m to n to m, but it's some subcollection of functions. But if you pick a random function from this class, then for all x in n, the distribution of h of x is uniform. Is uniform in u of n. Basically, it's distributed according to u of n. So for any x, should I specify the quantifiers the other way? For any x in the domain, if you pick a random function in the class, the image of that function on this fixed point is a uniform element in 1 to n. That's the first property we want. The second property we want is for every pair of distinct elements in the domain, if you pick a h from this, h of x1 and h of x2 should be independent. Equivalently, you can write this both conditions 1 and 2 together as for all x1, x2 in the domain, for all distinct x1, x2 in the domain, for all pairs of y1, y2 in the range. These could be distinct, need not be distinct. If you pick a random function h from the class h, probability that h of x1 equals y1 and h of x2 equals y2 should be exactly equal to 1 over n squared. This is what we want. We have an independent family of hash functions. So that's basically, this is the. And what we saw last time, we saw a construction last time. We saw a construction for the specific case when size of n was equal to, the size of the domain was equal to the size of the range, which was equal to the size of some finite field we are working with. For this particular case, and in particular, what was the family we had constructed last time? We had constructed a family HAB. It was indexed by 2 elements in the field, AB in F, and HAB was the function from F to F by mapping, which mapped X to AX plus B. It was this nice function. And last lecture we had proved the claim we had proved a nice thing. Once you state this object, the proof of this is very simple. We just proved that HAB is a pairwise independent. We didn't call it this, but family of hash functions. Okay. Who's typing fast anyway?
No. So I was just mentioning that, something that I find very useful to think of is that picking an edge from this family is like you're making a simultaneous choice for the image of all points on 1 through n together. And therefore, picking this edge from this family may introduce correlations between the value of a particular point in n versus some other point in n. And the above 2 points are 2 specific guarantees that you want when you choose this simultaneous choice at random. Firstly, that the image of any one coordinate should look completely uniform. And when you pick any 2 coordinates, that should look uniform and independent. That is, there's no correlation, but there are no guarantees at the moment specified when you choose 3 or more coordinates.
Yeah. So expanding on that, so let's look at one way of picking a pairwise independent family of hash functions. Actually, pick a completely random function. Let's look at how many bits are required for that, and let's look at how many bits are required in the example the way we constructed last time for the specific setting when n equals m equals size of field f. So if you had, let's look at the number of bits needed to specify a h in h. Specify h. So if you had picked it completely independently, so if you picked a completely independent function, then you need to pick a field element for every single point in the domain. So for every point in the domain, there are f points in the domain. For each of them, you need to pick a field element, and picking a field element will take you log f. So this is the number of bits one would require to specify the function. Whereas if you do it in the pairwise independent fashion, to specify the function, I just needed 2 elements from the field. So all I needed is to just pick 2 log f. That's the number of bits required.
So here, what you mean is that the above construction of a pairwise independent thing uses only 2.
Yeah, I'm talking about this. I'm talking about the construction that we saw about. Construction from last time. Yeah, I'm talking. That's why I was working with a f as this one. So I'm comparing the 2 situations. So this is you're saving a lot of randomness in this process. That's all I'm saying. It's a much more efficient way with respect to randomness. Okay, this was a specific setting of the domain and the range. Let's ask slightly more generally. If I want arbitrary m and arbitrary n, how do I modify this one? So let's look at, so the way we specified usually is from the domain to be any n and the range to be any m. So let's think of n itself. Let's look at a special case in which n is 2 to the n and m is 2 to the m. These will be cases that we'll care about. So I'm looking at functions of the form 0, 1 to the n to 0, 1 to the m. We can work with other settings also, but this will be nicer for this one. In this case, what we'll do is we will just, so let's look at, there are various cases now you can talk about n being equal to m, n greater than m, n put as an M. So let's start with the case 1, which is the easiest of the case when n equals m. Here you just set f to be the field, f to be g of 2 power n, and exactly the above construction will work. Okay. Case 2, suppose n is less than m. I want to say the above construction again works, but with a slight modification. What do you think we can do?
Sorry, I'm a bit lost. So, what are we trying to do now? Now we have some.
Sorry, I can't hear. Yeah.
Varun, your voice was very faint. Yeah. I think it's the same microphone issue of Zoom. Yeah.
Okay.
Okay, so Varun has a question. He's a bit lost what we are trying
No.
to do.
So do you follow the pairwise independent? So now I want pairwise independent function in specific cases of stating the input domain, stated it in general when the input domain is capital N and the output domain is M. And let's think of M being of the capital N being 2 to the N. Therefore, you think of the input domain as bit strings of length N and the output domain as bit strings of length M. So I want a family of pairwise independent hash functions that map an n bit string to an m bit string. This is what you want of the class of functions. How do you use our construction to get such an object? Now, if n were equal to m, then if you work with the field which is g of 2 to the n, our construction exactly satisfies the requirements. Now, depending on the context, n might not be equal to m. There might be some cases in which n is greater than m, some cases n is less than m. This one, I want to know how we can modify these constructions. In both cases, it's going to be a very simple modification to the existing set to get to this construction. I want to ask, can we modify, say n is less than m. Now the inputs, the domain size and the range size are different. How would you do? You just, if n is less than m, it doesn't matter. You pick the field to be you still set f to be equal to g of 2 power m. In this case, you get the function on a larger domain. You just ignore the value of the function on the larger domain. That is, if the function is, so you can think of, you want a function from 0, 1 to the n to 0, 1 to the m. So if you give, say I give a h of x, I go just, this is m, I get n bits. I just artificially add n minus m bits. I have the function h prime which works with n bits. I just add this
m minus n, but it's okay. Yeah.
Did I put m minus? I thought corrected it. M minus n. Is that clear? So you just expand the input to bits and do it. And now notice that even on this large input, the property was true. Therefore, it's going to be true on this setting too. That's case 2.
Sir, I have a question. So if I take the input as an n bit string and just modify whatever output I will get will be an n bit string, and then I trail it with the remaining zeros. After that, will that also be the same? Or?
Will that be uniform in the output? The output always has trailing so many bits.
Okay.
So it can't be uniform in the output. So you have to do it this way.
Yeah.
Okay. And yeah, so it won't be uniform. Yeah, it won't have the uniformity property. Therefore, we do this. In case the other case, what will you do? Now you can modify whatever you said. Now, if n is greater than m, what would you do?
We can project out the last code.
You just project it out. In this case, you work with f once again being g of 2 power n, and then you project it out. You h of x, you write it to be just h of x, h prime of x projected to the first m bits, or whichever m bits, and that will take care of it. So notice that how many bits do you require to generate the pairwise? It was 2 log f bits. So what I want to say is the number of bits required to generate H is just twice max of m comma n. It's 2 log f. In either case, it's twice max of m comma n. If you're a little careful, actually, you can do a little better than this. It's actually, in fact, make the observation. You can do it with max of m comma n plus n, and I'll leave it up to you to do it. But this won't be useful. But you can do this also. The same construction will do it. Okay. So in particular, I'm just going to abstract out all of this, stating that for all mn, there exists a pairwise independent family of hash functions which we'll call HMN that requires at most 2 max mn bits to specify any function h in H. And furthermore, strictly speaking, I had to say this function can be explicitly computed and all, which is true. I'm not just stating it because we never formally defined these objects, but this will be needed. This function is given these bits, you can actually, from the bit, you can compute the function efficiently and all, and that's because you do know the field multiplication and addition are efficient. Yeah, so this is the summary of what we did towards the end of last lecture, and there were comments in last lecture which said that you could extend this from pairwise independence to k-wise independence, and all of those extensions work. There were also questions on, is this tight? Is the number of bits required tight? And I mentioned here that it is max mn plus m. There will be a problem in the problem set where we'll more or less show that for certain settings this is tight. But this is the number of bits required. If you want a pairwise independent family, you need at least so many bits, and this construction achieves with so many bits. Okay. Any questions? We will move on to the topic of the day. Yeah.
One question. So the thing is, we had number of bits required to construct this hash family. So this f log f thing, right? Which you said how I didn't get it. So can you just repeat that? Like
no f log, not the 2 log f. You are asking the f log.
Yes.
No. F log 2 log f is the number of bits to specify this. You had to specify a and b.
Yes.
That was log f and log f each.
Yes.
Now suppose but this was this specific family of functions. Now suppose what I wanted to do is another way of specifying this pairwise independent family is just pick a completely random function of this type.
Oh, okay.
That's also obviously has this property. It's uniform. Its margin on every domain point in the domain is uniform. Every pair is independent. Not only every pair, every triple is independent. It has every form of independence. But how much do you need to generate that? For every element in the domain, there are f elements in the domain, you need to specify what's the range. So that's the total amount of randomness that you need.
Okay, got it.
Which in this world will be n log m. And we are doing
this is just a different way of saying there are totally n to the n functions, and to specify one of them, you need log that many bits.
Yes.
Yeah.
And this is doing substantially better. So if you notice that your analysis in some places requires only pairwise independence, you can shrink the amount of randomness. And this is actually, if you look at it carefully, in some cases, this is actually an exponential drop from f log f to 2 log f. Okay. So the next sort of 10 to 15 minutes, what I will do is, so some of you who has, so I'll sort of, we'll be I'll just introduce you some basic complexity classes that we will be talking about. We won't be spending a lot of time on these complexity classes, but it'll be useful. It'll be shorthand notation for various things we talk about later on in the course. Complexity classes. In particular, we'll be talking about randomized complexity classes. So you would have heard all of these phrases already. The classes like P, BPP, RP. This is not our RP. It's ORP and CPP and so on. Okay, so we'll just quickly define what these objects are, so that sometimes it's easier to write statements if we have these complexity. I don't have to write long statements. I have shorthand for them. So particularly, we're talking about algorithms. We're talking in this class. We're going to be talking about algorithms. We're talking about algorithms which run in a certain fixed amount of time. So we're going to talk about. We will say that a particular. And even before before I talk about algorithms, algorithms are generally for a problem at hand. So suppose I want to find, given a graph, I want to find the best, given a bipartite graph, I want to find a matching in the graph. That's a sort of a problem, a computational problem ask. But when we talk in complexity classes, we won't be talking of such sort of problems. These are sort of problems. You give me a graph, you find a matching to the graph. You give me sort of a network, you find the best route for the traveling salesperson problem or something. You can ask this. And we're going to ask about very much more specific problems in which the answers are only of two types. They are yes or no answers. I want to ask, is the matching of this size or not? Is the traveling route, is the best shortest route, is it larger than this value, smaller than this value? Is this number prime or not prime? So we'll talk about a specific class of things called decision problems. These are also more commonly called at least in the computational jargon, languages. So these are basically yes-no problems in which the answers are of two types. It's useful. There are too many L's over there. Yeah. It'll be easier to work sometimes when we talk about yes-no problems. So we will talk about complexity classes usually refer only to languages, decision problems. They don't refer to problems of the more general nature in which the answer could be like factorize this number. That's a problem. That's a specific problem. It's a search problem. You want to find the factorization. Find the best matching. That's a problem. What I'm asking is there a factor greater than a particular value or less than a particular value? Is the matching, is the best matching of this site? Does there exist a perfect matching or not? So I'm talking about yes-no problems. And complexity classes usually refer to decision problems. And one of the reasons for doing this is you want to compare different type of problems. And if the problems are each problem, certainly you feel as if you can't compare factoring to matching and all of these things to different problems. They seem like comparing apples and oranges. So we want to bring them of the same type. So we make them all into decision problems, and then you can talk of begin comparing them against each other. So it's sort of it's an easier way of expressing things. We will see that it's irrelevant why there are reasons for doing this, and we will not go into this in this class, in this course. And so you have a decision problem, and we'll say an algorithm. So first, let's start off with deterministic algorithms. So an algorithm is just some sort of computation, this one, which takes an input and is going to output A of X. And we are talking about languages. So A of X is either yes or no, or sometimes this is said as a problem whether accepting or rejecting this one. And deterministic is it doesn't toss any random points. It's a fixed. It's on every input. Each time you run it on this input, the run will be exactly the same as if you run it on the same input. So on a different, every run on the same input will always look the same. It's deterministic. It's completely fixed. There's no extra random points that it tosses. And we'll say that an algorithm A. So we want to further talk about the time complexity of algorithms. So T is some function. Okay, we'll say algorithm A runs in time T if for all inputs X A runs in time at most T of the length of X. You measure it in terms of the input length. The running time of the algorithm is measured in terms of the input length. To be very formal, I have to specify what sort of functions T I am allowed. This will also be a distraction for us. So the only T's that we will be talking about in this course are T's which are of the form like poly n. So some like n square, n cube. These are sort of n power c, or T's which are of the form exponential, 2 power n, 2 power n square. So we'll talk only of these. These will be the permissible T's. We'll have to talk about which functions T are allowed and all. This will take us too much of a distraction for us. So we'll work with this. And P is just, the class P is just the set of languages that have a polynomial time or polytime deterministic algorithm A. After that, if X for the essence for the when they put as X, or which we call, which is usually said as X is in the language, then the algorithm A of X accepts. If X is not in the language, then A of X rejects. I mentioned this. So when I say decision problems, this is mentioned by a language. There's some inputs are the S instances, some instances are no instance, and this is what I mean by the probabilistic class.
The term language refers to the domain of the input, or
So the term language, language is the domain. No, it's not domain. The domain is always the domain. So the domain of A. So let me say, so A, the domain of A is always 0, 1 star. It takes all possible input strings and outputs either accept or reject. Language is a subset of this.
okay. Okay. Yeah.
Yeah. For example, if you're doing primes, the domain is set of all strings. The language is the set of strings which corresponds to prime numbers.
Okay. Yeah.
And the algorithm is checking if it's prime or not.
Yeah.
Okay. So the domain for us always will be 0, 1 star or sigma star. If the underlying alphabet is sigma, we'll always, for most cases, we'll assume the underlying alphabet is the Boolean alphabet. So domain of all these algorithms will be 0, 1 star. And language is a subset of 0, 1 star. So I'm just going to say language is just this. A language is just some subset of 0, 1 star. That is assuming the alphabet is Boolean. What is the language? Language is just the cases on which the problem is yes. Everything else is no. Yeah. Okay. So now let's move on to randomized algorithms. So randomized algorithms, as we saw before, are algorithms which have two sets, which algorithm has the input X, but in addition to this, this algorithm also tosses points. So let's explicitly say that it gets this other point R, and then it A of XR is once again, this is either it says accept or reject based. So a run involves an input and a random point. It takes both of these as inputs. This is the actual input. This is the random coins. And then based on these, for now, for the next 5 minutes or so, we'll consider algorithms which for every input, irrespective of the random coins, runs in a fixed polynomial time. That is, the run of the algorithm is not the amount of time the algorithm takes is not a random number. It's a fixed polynomial time. Okay. So we will consider a slightly general class a little later, but for now, let's work with this. That is, we'll work with algorithms A. That run in time, in a fixed time for all inputs of a particular length, irrespective of the random coins. So the randomness, there's no probability in how long the algorithm is running. The only probability is how the algorithm, what the algorithm outputs on the input. And now we will talk about, so therefore, if the algorithm is running in polytime, notice that the number of random coins it can access is also polynomial. It can't access because it's only running for polynomial amount of time. The number of coins it can talk, number of coins it can read will be only polynomial, because the algorithm is only allowed. So we'll talk about the class which is RP. This is short for randomized polynomial time. Randomized polynomial time algorithm. So RP is the set of languages for which set of languages L, for which there exists a randomized polytime algorithm A with A satisfying the following features. What are the properties I wanted to say? If X is in L, then notice I cannot say A of XR has to be accept, because that depends on the value of R. So I want to say A of XR is accept with high enough probability. This happens, say, with probability half. Now you can ask me what's the importance of half here. We'll come to that in next one. And if X is not in the language, then I want to say, actually in this case, I'm going to say that its accepts is 0. That is, it always rejects. You can ask why is it this way, but this is the definition of RP. Is the definition clear? So RP is in some sense randomized polynomial time algorithms which have one-sided error. The error is only in the S instances. The error is never in the no instances. So when the algorithm accepts, you certainly know that the problem is in the language. It can never accept a no input.
So the running time of these algorithms are upper bounded by some polynomial in
the input length.
In the input length.
Yes. That's what when I say runs in polynomial time, that's what I mean. It's a fixed polytime in terms of the input length. Okay. And because of that, the number of randomness is also polynomial, because it can't read in polynomial time, it can't read more than polynomial number of random bits.
But it could be the case that the number of tosses depend on the input.
Yeah, it could be. In some cases, it could decide to toss a coin. Some cases, it doesn't toss a coin. It could depend. Yeah, number of coin tosses. But you might as well say it tosses for every step of the algorithm. It tosses a coin. It just doesn't use the coin.
Okay.
Yeah. So yeah. Okay. So RP is this. RP is sort of one-sided languages which have one-sided randomized algorithms. One-sided error. The error is on one side, and the reason we sort of notice, if you look at and co-RP, the accompanying class is the same one, is similar to randomized polynomial time, except the error is in the no instance. That is, co-RP is same as above. Same as above, except that if X is in L, then the probability of acceptance is, it always accepts. This is 1. If X is not in L, then the probability of acceptance is less than or equal to half. Okay, it's just a complement of this previous thing. And if you recall the algorithms which we had said when we had described beginning, like primes and all, are actually problems in primes was in co-RP. Also polynomial identity testing was also in co-RP. These are actually problems in the algorithms which we had specified in the first lecture are actually co-RP algorithms. They were one-sided. In the yes case, they are actually, whenever it said it was a prime, it was a prime. Whenever it is a prime, the algorithm will always output it as a prime. If it's composite, it could mess up. It could, with high probability, it will say composite, but it won't say necessarily composite all the time. But the moment it says composite, you do know that the algorithm was, that the number is composite. It will never say composite on a prime number. Okay. So far, so good. Okay. So one question you should ask. Yeah. One question we have. So what is a question which we can ask is, why did we choose half as over here? Notice that half is, I could have put 1/3, 1/4. Notice that if you have a randomized algorithm, suppose I give a definition with respect to half. Somebody else comes and says, I will use 1/4 as this one. Or is the corresponding class going to really change? I want to say no. Because suppose somebody gives me a thing with probability, in the yes case, it's half. And somebody else wants to say in the yes case, I want this number to be 3/4. How would you improve the probability of, how do you reduce the error from half to 1/4? In this case, I'm saying the error is at most half. If I want the error to be at most 1/4, how would you reduce the error?
Repeated iterations and then take the majority.
Yeah, so repeat it say t times, and then take, what do you take?
Majority.
Do you have to take majority? Suppose you repeat it t times, and on some number of times it says accept, some number of times it says reject.
If it says reject, then it is definitely a reject, right?
Yeah, because these are one-sided error algorithms. If it says reject, you know it's a reject.
So the error would say t times the error would be half to be t.
No. If it says accept, it is always accept.
Yeah, if it's
in RP, the mistake is only in the no answers.
No answers. So if ever says accept, you accept.
Right.
Yeah.
So
therefore, in this case, you don't have to do majority. Just simple. You run the algorithm so many times. If it accepts even on one of the runs, you run the algorithm independently on t trials of the t independent random coins. If on any one of the runs it accepts, you accept. If it's going to reject on all of them, you reject. So so I would just want to ask, let's look at error reduction for RP. One needs to reduce the error in RP. What do? You just repeat. So if you had the algorithm A, you repeat. So A of t is just pick. So on input X, pick random coins R1, R2, RT, run A of X1, XR1, XRI, A of x RT, accept if any one of them accepts, and reject otherwise. So let's quickly see if x is in the language, what's the probability that AT x, now I'm going to put R as the big random, this accepts. I want to ask this, and if x does not belong to language, what's the probability? This R is just R1, R2, R2. It's a combination. So what are these two? So suppose it was originally half. Let's ask for the bottom case. What will this be? If x is not in the language, if I repeat it t times, what's the probability that any one of the repetitions will accept? We are in this case. I'm in this case. Originally A has this property. If x is not in the run, the probability accept is 0. So what's the probability that any one of the R runs accept, the T runs accept?
0 again.
It will still continue to remain 0. What about this one?
It's greater than 1 minus.
So it's going to be greater than 1 minus
half to the t.
Half to the t. Therefore, you can just get the error down as low as possible. You can make the error, in fact, inverse exponential. And so this half, all of this, this one is saying is this half. So the gap over here is in one case it's half, in the other case it's 0. This gap, it could have been any number to begin with. You can get the error down. So here the error was. So let me to make. I can make the gap as close to 1 as possible. I can make the exponentially. That is in the no case it will still be 0. In the yes case you can make the number 1 minus an inverse exponential quantity. So that's what I said. So this, with the choice of this constant here is completely irrelevant. All of these would have just changed the number of runs the algorithm could have done. And because you're allowed, RP refers to polynomial time, repeating it is not going to change the class. Therefore, this half is not usually mentioned. Book to book will use some other constant, whichever they want to, and they're all it will refer to the same class of languages. Okay. Any questions? Okay. Okay. So that's RP co-RP, but sometimes more general, both of these were problems with one-sided error. You can have problems now. You can have problems which have error on both sides. By the way, you should. One thing which we should see. Let me first talk about. We want to move to algorithms which have algorithms with error on both sides. With error on both sides, or with possibly error on both sides. So this refers to the class BPP. It's just L belongs to BPP.
Why is there a separation between RP and co-RP? Like, it seems very symmetric, right?
So it seems what is symmetric. So for example, polynomial identity testing. Let's look at that algorithm for polynomial identity testing. Okay. What is the algorithm? It just picked. I gave some two polynomials in some circuit form, and I wanted to check if they were equivalent or not.
Yeah.
If they were equivalent, no matter which input you pick, they will always be equivalent. So in that case, you would always get accept. If they were not equivalent, if you were lucky, which would be most of the time, you will pick a point on which they are not this one. But notice, I do not know how to flip the behavior the other way around. The natural algorithm I give you gives you a co-RP algorithm. It doesn't give you an RP algorithm.
Mm-hmm. Okay.
It would be good to find out if there's an RP algorithm for polynomial identity testing. I don't know how to construct one there. So it looks, the definition is symmetric, but the definition is symmetric in the sense it depends. In some cases, you might be able to err on one side, but not on the other side. For example, primes, the natural we didn't see any of the randomized algorithm, but the usual randomized algorithm for primes, which is the Miller-Robin or the Solovay-Strassen, are actually co-RP algorithms. They are not RP algorithms. Of course, today now there is a deterministic polynomial time. It's actually in P, not just in co-RP. This one, but it's P. But the original algorithms were co-RP algorithms. They're not RP algorithms. And it's important, this distinction. The error will happen on one side, depending on how the algorithm works. Does that answer your question, Sushant?
Yeah.
So L is in B. So this depends when you're designing the algorithm. Sometimes it might err on this side. Sometimes it might err on that side. So of course, P is in which there is no randomness and it doesn't err on either side. The algorithm which we saw for polynomial identity testing error on one side. BPP is a more general class which allows error on both sides. L is in BPP if there is a polytime randomized algorithm A such that I'm going to allow error on both sides. Probability R A XR equals accept should be greater than 3/4. X not in L, the probability R A XR equals accept should be less than 1. Okay. So we will talk about error reduction for BPP shortly, but before that, I wanted to, once again, you should ask me what does, one natural question is why is 3/4 and 1/4? What can't I put 2/3, 1/3? Can I put 9/10, 1/10? And put this, and we'll just see that this definition doesn't really care about this. Because we're allowing polytime, repetition will help you, but that will take a little proof. I'll wait for 10 minutes and we'll see the proof for this. See the proof for this. Okay. Questions on the definition so far?
All of this was on the binary alphabet, right? Like, or do you have some, like, how does it vary if the alphabet changes? Like,
no, the alphabet changing because moving from one alphabet to another alphabet is just an encoding thing. You can always assume things are on the bilinear alphabet. So the alphabet doesn't cause an issue over here at all. It's everything is in terms, but the encoding, you must be careful that you're encoding succinctly. You're not, so there are different ways to encode. And for example, encoding, whether you're doing in binary or unary, this matters. The alphabet has to be at least 2 elements in the alphabet. That's what we need. If the alphabet has just 1, that will change the game completely. So 2 onwards, the alphabet size is 2, then it doesn't matter. All of these are the same more or less. Not more or less. All of these are the same. They're exactly the same object. Okay. There's a lot of chat messages. I'm not reading the chat. Yeah. So if there's anything important. So we'll come to why it's 3/4 and 1/4. But before that, I want to talk about, let's look at how are these classes determined. So we had P. Certainly P is contained in RP. P is also contained in co-RP because these are just, and then both of them are contained in BPP. Okay. But I want to now talk about a slightly different class called ZPP. By the way, I should just mention BPP stands for bounded error probabilistic polynomial time. It's unfortunate that it could not be called probabilistic polynomial time PP because that name was already taken for a different complexity class before BPP was defined. PP also stands for a complexity class which we won't be studying in this course. PP was reserved for it, therefore they had to come up with a different name called this one. It's called BPP, which is bounded error probabilistic polynomial time. Yeah, so just that BPP became a more popular class much later on, but the name PP was reserved for something else, so it's called PP for that and BPP for this. Now I'm going to talk about another class called zero error. We won't be spending much time on this class, but you would see this in books. So I just mentioned the zero error probabilistic polynomial time. So this is the one in which, so far we mentioned that the running time of the algorithm is a fixed polynomial, not dependent on the randomness. It has no, the running time is not random. Now we're going to, but the performance of the algorithm, whether it accepts or rejects, is a random variable. Now I'm going to change the game. I'm going to sort of say, I'm going to allow the runtime of the algorithm to be randomized, to be a random number. But the output has to be correct all the time. You can ask, of course, you can have randomness in both, and we'll come to that a little later. The output always has to be correct. So so I will say, we'll say that L runs in ZPP if there exists, if there is a probabilistic polynomial, randomized polynomial time algorithm. So what do I mean by this? A randomized polytime. What do I mean by polytime now? Polytime algorithm A that runs in expected polynomial time. So it is its expected running time when you take average over all the random points should be polynomial. It could take, on some coins, it could take very, very long. It could even possibly run exponential, but the expected runtime should be polynomial. Runs in expected polynomial time. And as before, if X is in the language, then but on the other hand, I'm not going to allow it to make any error. A of XR is accept should be equal to 1. And if X is not in the language, is equal to accept should be 0. This is what ZPP denotes. And we won't do this, but it is not hard to see. There's a proposition that ZPP is actually just the intersection of RP intersection core. I can put this in the homework. It's not hard, but that's one easy to see this. It's also not hard to see ZPP is in BPP. So this picture, the reason I stopped this picture was because of this. ZPP over here, RP is contained here, this is contained here, that's contained. That's the picture. Questions?
No, the picture was off.
Sorry.
Yeah.
Sorry. This is, the picture is off. This picture. This is contained this is contained this. ZPP is over here. And P is over here. Yeah. ZPP is the intersection of RP intersection.
ZPP is the intersection.
Yeah.
So only the first statement of the proposition is, that implies the second already, right?
Which one?
First implies the second.
First implies the second. Once you realize ZPP is in a RP intersection for RP, it's clear. But you don't need the first to prove the second. You can see that. Because it's expected polynomial time, you can basically say you run it for twice the expected this one, and then if you don't get an answer by then, you just flip a coin and answer according to the coin. Okay, so that will easily show you ZPPs and BPP. The first one is a stronger implication. Okay, so these are this one. So what I will spend, I have about a half an hour more. We spend on B. So the thing I'm going to spend is on BPP. We talked the error bound is 3/4 and 1/4. Question is, can we reduce this error? The error was 1/4 in either case. The error in this case was 1/4. The error in this case was also 1/4. Whether we can get this error down. And in the course of trying to understand this, we will talk about various basic probabilistic inequalities that we will need In particular, we'll talk about the Chernoff bound. Questions? So what we'll do next is particularly we will talk about error reduction. Error reduction for RP was trivial. We're going to talk about error reduction for PPP. That's going to be our talk. Okay, so let me start off. So we will need some basic probability inequalities for this. Tail bounds. I won't prove them, but we'll take them off the shelf. The first is, many of you would have seen this. The first is Markov's inequality. Says that if X is a non-negative random variable, with finite expectation, E of X, then the probability that X is larger than alpha is less than or equal to expectation X by alpha. This is an easy, it almost follows from the definition of non-negative random variables and the definition of expectation. I will leave this. Most of you have seen it. We'll take this. This will be a basic thing we'll use. Next one, this is the first of the inequalities I will need. The second one is what is called Chebyshev's inequality. By the way, these names are not standard. In our community, we call this Markov, Chebyshev, and Chernoff. Things in some places, even Markov's inequality is called Chebyshev's inequality in this place. So these names are not standard. It depends. It depends on the community persons who are doing it. There will be lots of such confusion among the names. But this is what in this
spelling is also not standard.
Yeah, spelling is not standard.
Yeah, there are some TCH in some places. And so.
Yeah. So I think in computer science, when they use TCH, they refer to a different inequality. It might be the same Chebyshev. So here, this is the inequality which says that suppose X is a real valued random variable with both finite expectation and finite variance. By variance, the expectation is just expectation of X. Here, variance of X is expectation of X square minus expectation X. Then probability that X differs from the expectation by more than epsilon is less than or equal to variance of X by epsilon square. Put less than or equal to. And this is an easy application of the Markov's inequality. It easily follows from Markov. It takes 2 minutes. Let's try to save those 2 minutes, but you can check that out. Right? I'm assuming you would have seen this inequality true. The next one, which we'll see, is a Chernoff. It's called the Chernoff bound. So let x1, x2, xt be t independent, but unlike before, these are bounded. They are 0, their value is 0, 1 valued random variables. They are bounded. They are not arbitrary real valued random variables. And let us define the random variable x bar, which is the mean of these xi's. So it's summation xi by t. And let mu denote the expected value of this average of these guys. Mu of x bar. So x bar is an average of them, but it is not. It is also a random variable. And mu is the mean of this average random variable. What we want to ask is, what is the probability that x bar deviates from its mean by more than epsilon? And this happens to be twice e power. It sort of deteriorates as it improves exponentially as you average over, as you take the sum of more and more number of variables. It's a Chernoff bond. There are various forms of the Chernoff bond. We use this Chernoff bond. Okay. Questions on this? So based on this, we will let's revisit the L and BPP, the error for BPP. So I want to say, so we will use Chernoff. So what next is going to be, we'll use Chernoff bound. Chernoff bound to reduce error in BPP. Okay. So let's just go back to this one. Let's look at the definition of BPP. The way BPP, so I'm going to say this one. Let's talk about this. The error in the algorithms over here is 1/4. So this was BPP with error 1/4. The error in the S case and the no case is 1. Of course. I want to say Chernoff bound tells you that the following things, that is, the following three are equivalent. Three statements. Equivalent. 1, L is in BPP. That is, error is less than or equal to 1/4. 2, L for every polynomial P of n, L has a randomized of the two-sided error algorithm with error extremely small, with error less than or equal to 1/2 to the P of n. Extremely small error. The error can be made exponentially small. True. Other, there is a poly Q such that L has a randomized polytime algorithm with error less than or equal to half minus 1/Q of n. The error is just barely, that is the S case, you accept with probability half plus Q of n, and the no case you accept with probability at most half minus Q of n. Therefore, it's barely better than random guessing. Notice if I had said half, then you can ignore the input and just toss a coin and say half. I'm saying in the third case, the algorithm does barely better than random guessing. The first case in which the algorithm just makes some constant amount of error, that's the first case. The second case, the algorithm performs extremely well. The error is like inverse exponential. And then the third case, the error is just barely better than, the algorithm is just barely better than random guessing. I want to say all of these three definitions of BPP are actually the same. This one, there's no change. These are all equivalent definitions of BPP. And certainly some direction should be true. So which direction is true?
So before that, I have a question.
What? This should be the easy. This should be easy. 2 certainly implies 1, certainly implies 3, because the error is this. The 2 has the best error. Certainly, if you have inverse exponential error, that also means you have constant error, which means you have better than solved. Abhishek, what was your question?
Yeah, so in 2, when we write that for all polynomial PNL has a randomized algorithm with error, blah blah. So do we mean when it is allowed to run for PN time, or
No. So the algorithm will have to. The algorithm might run for a different. It might run for a longer polynomial amount of time. For every polynomial, there's a different algorithm which possibly takes another polynomial amount, which possibly is larger than Pn, and gets this.
So maybe the right way to think of it is like, let's say you tell me your tolerance for error is 1/2 per P of n.
And I will
then
give
there is an algorithm which will run in polynomial time. This polynomial may depend on P of n, such that this algorithm solves L with only the error that you want.
Which is exactly the order in which I have written it. For every polynomial P of n, there is an algorithm. That polynomial time of the algorithm might depend on the error tolerance that you want.
Okay.
Yeah, and 3 is more like someone gave you an algorithm which barely does better than random guessing. And given such an algorithm, you can modify it to get the guarantee in 2. You might say that half minus 1 over Q of n is just way too much error. I can't tolerate that. I want error 1/2 per P of n. And there's a procedure to do that.
Okay. And the idea is just, I think Amik mentioned this for RP error reduction, run the algorithm several times over and take the majority value. So this is just, so we need to only show 3 implies 2. 3 implies 2. That is, we have an algorithm that works just better than random guessing. It's a polynomial advantage over random guessing. So let A be the algorithm. Let A be the randomized algorithm from 3. Now construct the algorithm B. Let's, as before, let's construct an algorithm which let me call it AT, which works as follows. On input X is exactly similar to what the amplification algorithm we've done. Pick R1, R2, RT, which are T independent random points. And run A of X R1 all the way, run on the algorithm one. Do T independent runs of the repetitions of the algorithm on the T different random points, and accept if the majority accept. Okay. People with me? Now what we want to ask is, I want to ask what's the error of this algorithm A of T. So now let's come up with a random way. So we want analysis. I want to analyze the error of AT. So let's define xi to be the random variable. It will be a 0, 1 value. It's going to be a 0, 1 valued random variable. And xi is one, if A of X Ri is incorrect and 0 otherwise. So what do you know? What do we know about expected value of Xi? Expected value of Xi, this is exactly the probability that A of X Ri is incorrect. And this we know is less than half minus 1 over Q of N. Now I want to ask, what is the probability that AT, that is fix, all of this is error, so fix, all of this is fix a particular input, fix some input X in the, fix an S in this one. Probability AT is incorrect on XT.
Sorry, what do you mean by XT? It's just X, right?
Sorry. On the input, on the small input X. On small input X. Yeah. Want this? When is it going to give? If majority of the answers are wrong. In particular, if this is exactly the probability that summation Xi is greater than greater than or equal to T by 2. Which is certainly less than probability summation Xi by T minus half is greater than 1 over Q. This is certain. I've just rewritten this one. That is this deviation. Sorry, this is not how I wanted to. Sorry, this is not how I wanted to write it. This is not how I wanted to write it. The probability summation Xi by T minus half minus 1 over Q. First, let me write it this way, and then let's 1 second. I want to skip 2 steps so we can do it. This is great. I want to say this is greater than or equal to half. I want to apply Chernoff bound, so I want to compare summation Xi by T to the average. What is the average? The average is half minus 1 over Q of N. So this quantity is the same as is this. So this was an equality. This is less than or equal to probability summation Xi by T minus the mean. The mean is half minus 1 over Q of N. This is greater than equal to 1 over Q of N.
The mean is less than equal to half minus Q by N.
Yeah, you probably don't want to put an absolute value here.
Here, this statement, which is certainly less than or equal to probability X bar minus mu is greater than or equal to 1 over Q of N. If the mean
by the way, so I think the way, I mean, okay, so just, I think the Q of N is, no, it's fine. Oh, sorry. No, it's fine. Yeah.
So this by Chernoff bound is less than or equal to twice exponential in minus T by 4Q square. So if I just say choose, this I can make it to be less than 1 over 2 to the P of N. If I set T to be equal to, if T is some huge constant times P of N into Q squared of N. So it just tells you I can use the Chernoff bound to reduce the error. Just repeat the algorithm several times over and take the majority. That will take an algorithm that just has polynomial advantage to an algorithm that makes exponentially small error. An algorithm which has just polynomial advantage over random guessing, that's sufficient to, you can just repeat the algorithm several times over and get something which has exponentially small error. Okay, Any questions on this?
Yeah, can we go to statement 2 one more time?
The entire proof or the statement of the theorem?
The statement.
This one?
Yes.
Yeah.
So suppose I had written for all epsilon greater than 0, L has a randomized algorithm such that the error is at most epsilon.
Yeah.
So I want to see how that statement is different from 2.
How that statement is. So 1 over 2 to the Pn. So here.
So Prahladh, can you go back to that statement again? So I think the word that's missing here is randomized polynomial time algorithm.
Two-sided error, poly time.
Yeah.
Yeah.
So would this answer Abhishek's query?
No, I still don't see the.
So let's see how many. Now, what is the, let's look at, what is the running, okay, this is this. What is the running time of AT? It's the running time of A times P plus computing majority. Let's assume computing majority is easy. I'm not going to, it's one fixed polynomial. So it's basically this one. So it's
running time of A.
Running time of A, sorry. Running time of A times T. So this multiplicative thing, T should be polynomial. If T is super polynomial, you will not be able to, this will not remain a polynomial time algorithm. That's why I can get the error only to inverse exponential. I cannot make it inverse doubly exponential or something. Abhishek, does that answer your question now?
Yeah.
Yeah. So I can only get the error down to inverse exponential. I can't get it to smaller than inverse exponential because then I'll have to run the algorithm. If I want to get the error algorithm to have error epsilon, then I have to run it log 1 over epsilon times. And if I want log 1 over epsilon to be polynomial, epsilon has to be inverse exponential. It cannot be smaller than inverse exponential.
Yeah.
That's the, yeah. So the missing thing was, as RP said, this is important. These are the important things over here. This one is one, but this is polytime is important. That's okay. Okay, so you can reduce the error. Now I want to say actually, this repetition is nice, except it. So let's look at this. Let's look at this repetition. I want to look at this one. So this we repeated we ran independent. This error reduction. So what happened here? It was a T repetition of the algorithm. Repetition of algorithm A. What's the number of random coins or random bits used by algorithm AT? It's exactly T times the number of random bits used by A, because we run T independent times. And this is because we use Chernoff bound, where Chernoff bound needed all the things to be independent. Now you could ask, can I get a similar performance in which I didn't use independent coins, but say I used pairwise independent coins? We could ask the same question now, coins, because that's one way of trying to improve the randomness. I want to get the same performance, but with a lower number of this one. So we can ask what happens if I use these coins which I had used, this algorithm, these coins which I had used over here, were not independent random coins, but only pairwise independent random coins. We could have used the pairwise independent family to generate these coins. Can I use them instead? Now, we ask, firstly, the same analysis does not hold because we are using Chernoff bound. Chernoff bound works only for independent. So we have to ask a similar tail inequality for pairwise independent random variables. So let's try to find out if we can get such a tail inequality. So I want to ask, so question which we're going to ask now is, what if R1, R2, RT were only pairwise independent? that's the question I want to ask. So let's write a tail inequality for pairwise independent random variables. Next would be, right, tail bound for sum of pairwise independent random variables. As before, let x1, x2, xt be not independent but pairwise independent random variable. Let's say put bounded again, say 0, 1 random variables, 0, 1 valued random variables. We define as before, x bar is the average of them, 1 over t. Mu is expectation of x bar. I'm going to ask the same probability that x bar minus mu is greater than epsilon. I want to put a bound on this. So here, what we will now do is this will appeal to you. We will use Chebyshev, and you'll see why we'll use Chebyshev. So I only have pairwise independence. I only have pairwise independence, so I don't have full-fledged independence. So let's compute what I can't use Chernoff bound. So I can use bounds which only involve pair of random variables. That is this one. So variance is one such quantity. Variance is the thing which involved only pairs of random variables. So let's see if I can calculate the variance of. If I knew the variance, I could apply Chebyshev's inequality. So let's see if I can compute the variance of x bar. This is the variance of x bar is variance of summation xi t. What is this? In this, if this happens to be this, but we want to actually let's just open this out. How do I want to prove this? This is variance of this. This is expected value of. Firstly, let me pull out the one way. Okay, let's say it's expected value of summation xi by t whole square minus summation xi by t the whole square. Okay, this is expectation of. So let's take out a 1 over t square. 1 over t square will come out in all of them. This will be expected value of summation xi xj when I open out the summation. So I less than or equal to j. Sorry, sorry, not I less than any pair of ij minus 1 over, there's a 1 over t square out there again, summation expectation of xi the whole square. This is 1 by t square. What is this? This is expectation of, this is expectation over I summation xi square. This is when I and j are equal. Otherwise, for I less than j, this is
plus
expectation xi xj minus summation expectation xi expectation xj. This is just once again 1 over t square This is summation I expectation xi square minus expectation xi whole square. So from here, I'm picking up i's and j's which are equal. I'm picking that up. So that's contributed to this. Then I have plus I not equal to j expectation xi xj minus expectation xi expectation xj. Now what happens to this? This one, the nice thing about it is because of pairwise independence, expectation xi xj is the same as expectation xi into expectation of xj. So these terms cancels. The only things that will survive, this is the only place in the proof where I use pairwise independence. This is exactly summation I. So the second thing completely cancels out. All I'll have is this. Because of this is due to pairwise independence. And notice that this is just 1 over t summations variance of xi.
1 over t squared.
Over t squared. Okay. So now let's go back to this one. So hence probability x bar minus mu is greater than or equal to epsilon. This by Chebyshev is less than where x bar by epsilon square. Which is what? Which is 1 by t square summation variance xi by epsilon square. Now this is less than or equal to 1 over t square epsilon because the xi's are bounded 0, 1 bounded random variables. Their variance can be at most 1. 1 second. What happened? No. Sorry. So I have this. So the summation. So it is summation 1 t square epsilon square. That is, since each variance of xi is at most less than or equal to 1. Therefore, this is 1 over t epsilon square. Okay. So if I had pairwise independence, then the number of repetitions. So similar, where I wanted to reduce the error down to inverse to a particular value. Say I want to reduce the error from I want to make the error delta. In Chernoff bound, if you wanted to make the error to be what happened here, this was the bound error in Chernoff bound. If I wanted to reduce the error to the Chernoff bound error was, let's just go back to where was the Chernoff bound statement. If I want to reduce the error to delta, I'll have to choose t to be something like 1 over epsilon square log 1 over delta. So in Chernoff bound, so let's say in Chernoff, to reduce error to delta, we set t to be something like order of 1 over epsilon square log 1 over delta. But with pairwise independence, in order to reduce error to delta, we need to set t to what? T to 1 over epsilon square delta. So the dependence on epsilon is the same, this one, but the dependence on delta over here is considerably weaker. So on one hand, we gained in the number of random points that we need to do it, but we lost in the dependence on error. So there's a Chernoff versus Chebyshev trade-off. When in the sense that if you use pairwise independence, the number of random points you use is considerably lower, but you pay for it in the sense that the pay for it the number of times you do it. This is like 1 over epsilon squared delta. We will see this more quickly when we do sampling. So there's an advantage with using pairwise independence. You save in the number of random points, but the reduction in error is much slower than what you would get with independent random points. So the trade-off, and sometimes we need to use both of them. Sometimes, because we need sometimes to reduce error, reduce random bits, we need to use both. But it's good to have both of these in mind. In Chernoff, if you want to reduce the error, the dependence on delta is reduce error to delta. The dependence is log 1 over delta. If you use pairwise, the tail bound for pairwise independence, the dependence is 1 over delta. There's an exponentially weaker this way. So this is basically, it's because you're having an advantage in one, you're paying for it in the other parameter. And you will see this in detail when we do sampling. That's just be an application of the statement which I have seen so far. Any questions? I will stop with this, but answer any questions if there are.
So just that at the moment, it's not clear that the number of random coins is actually smaller, right? That needs a calculation.
It needs a calculation.
Yeah.
It's a calculation.
Because the point is, in order to get the same error reduction, you now need a lot more samples than what you needed earlier. But somehow intuitively, we know that generating many samples using pairwise independence should be very efficient. But this is something you need to calculate. Like if you wanted like T many samples where T is according to 1 over epsilon squared, 1 over delta, but you only insist on pairwise independence, how many random bits do you need? Versus you want 1 over epsilon squared log 1 over delta samples, but you want completely independent things.
Yes.
So, yeah.
Yeah. We will do this when I will state this more explicitly when I state the sampling question. Yeah. So Varun had a question, or?
Yeah, the question was, are there applications that use the fact that Chebyshev works even for the weaker situation where every pair has covariance 0, but not independence?
Exactly, independence, no?
So I'm confused. So covariance 0 is independence, no?
If expectation xi xj is equal to expectation xi into expectation xj, that
Not
is
necessarily, right?
Oh, right. Yeah, that doesn't necessarily mean that the probabilities are
independent. Yeah. Yeah, this is all that we need. This is all that we need. And yeah, for 0, 1 random variables, which is what I'm looking at, they are the same. But it's not true for real valued random variables. So, yeah, for 0, 1 valued random variables, they are the same thing. Expected, yeah. So for this particular setting, there is no independence and covariance being 0 is the same thing, but not in general.
Yeah, but I don't have an answer to Varun's question that if there are applications that use the weaker form.
Yeah. Weaker to
Y. So I had a question.
Yeah.
So do we know how to generate like negatively correlated random variables if not independent or pairwise independence? Because even if they're negatively correlated, the same Chernoff bound would work, right? So Chernoff bound would still hold for weaker dependence, but it's
but isn't that only for one of the tails and not for the other or something of that sort?
Oh, right. Yeah. For one of the tails.
Sorry, I didn't get your question. Like, I didn't get the question.
So the proof of Chernoff bound doesn't actually need full independence. It only needs the fact that they are negatively correlated.
Again, that depends on which tail, but yeah.
Yeah.
Yeah, actually, I'm not entirely sure.
I'm not sure about that too. But I haven't seen an application in which there are places where you do. For example, I mentioned this. So I don't know reducing randomness, but I've seen places where these negative correlations have sort of helped. For example, the max cut application, I told you that the expected thing gives you half, but you can actually show that you can get half plus 1 over n. That comes by picking the random variables in the hypergeometric distributions, which are negatively correlated but not independently you get it that way, and that's what will get you the bound. So there have been some applications. I do not know in the context of pseudo-randomness if there are applications further. Okay, let's stop with this.
Okay, so I'll stop the stream.